focus on IC package layout with a real emphasis on strategies to assess electrical performance assessment early to streamline the design flow. The presentation will be given by Kevin Reinbold. He is a marketing manager at Sigrity with years of experience in IC package layout. And then there will be a demonstration by Dave West, who is a longtime Sigrity applications engineer. So with that, take it away, Kevin.
Great. Thanks, Leslie. I'd like to welcome you all to our webcast on integrated package layout and assessment. This is Kevin Reinbold speaking, and with me is Dave West, who will be handling the demonstration a little bit later. As Leslie mentioned at the beginning, as far as any questions are concerned, you have a chat capability, so please take advantage of that to submit your questions, which we will deal with at the conclusion of the webcast. In this webcast, we're going to profile an approach that we've pioneered that brings package layout and electrical assessment together in a way that provides the package layout team members actionable information for design improvement throughout the layout process. To start, we're going to take a look at the package design flow. I'll then introduce you to the UPD product. We'll spend some time talking about performance assessment with a quick overview and demonstration. We'll conclude that with some layout functionality in UPD, and then we'll address your questions and answers at the end. So one attribute of the package design process is that it consumes calendar time from concept to design, and it requires engineering resources throughout that process. Now, the ultimate goal of that process is the delivery of a successful package design that meets the specs for things like electrical performance, for cost, for size, and so on. We also need to deliver a physical design database of the package, as well as the electrical model of the package. Now, achieving these goals requires the coordinated effort of multiple people with different skill sets that span multiple departments, and in some cases may even span different companies. This process is characterized by multiple iterations back and forth between the different groups, with one of the challenges being clear communication of the changes that need to take place. In this webcast, we're going to focus on the portion of the process between layout and analysis. From day one, UPD has been built to address the design and analysis requirements of the broadest range of advanced IC packages. Its underlying architecture inherently understands advanced packaging concepts and design objects, resulting in optimal functionality and design flow. It supports both single and multi-die configurations using wire bond technology, flip chip, or a mixed attachment technology. It also supports stacked applications as well as advanced lead frame type packages such as QFNs and VQFPs. Now, one important point I want to emphasize is that companies that rely on outsourced design and assembly services often find themselves dealing with multiple versions of the same design, since these manufacturers are reluctant to share design databases with competing foundries. Using UPD, a company can lay out the design once and send the same database to all its suppliers, ensuring consistent package performance regardless of the manufacturing source. UPD is developed specifically for advanced package design and has an inherent understanding of connectivity and design constraints. Its design flow, its user interface are presented in a logical progression that's natural for package layout. One example of this is the use of task-focused workflows that help guide novice or casual users through a specific process. And we'll see a really nice example of this in the power assessment demo portion of today's webcast. Now, if you're familiar with other Sigrity tools like PowerSI or Speed 2000 or Extract IM, you'll notice many similarities with the UPD user interface, which really can help accelerate the learning process for a new user. UPD also empowers the casual or analysis-oriented user to produce and evaluate what-if scenarios to evaluate electrical performance and then quickly iterate the layout if needed, and being able to do so all within one tool. In most cases, the IC design team has a rough idea for package parasitics that may be communicated to the package design team, or more likely or more realistically, probably to the person responsible for analysis and model generation. Now, this information can include things like the parasitic and coupling data for signal nets, resistance and inductance information for the power delivery nets. The traditional approach to verify the performance specification usually results in a flow where the layout and analysis are done by different people using different tools that are most likely from different vendors. Very seldom is it that we see the performance information incorporated into the layout process. More often, it's looked at as a post-layout verification step, which has drawbacks. Those drawbacks can be things like iterations that can impact cycle time and the ability to clearly communicate the necessary layout changes. Now, we believe that one of the reasons for this approach is the lack of actionable information during the layout process, and information at a level that is easily understood by a broad range of layout engineers. At Sigrity, we're pioneering a new approach based on the concept of assessment. If you were to look in the dictionary for a definition of assessment, you would find that it says, a judgment about something based on an understanding of the situation. What this means to UPD is the ability to determine the quality or the viability of a package using a combination of numerical and qualitative information that's derived from the design. It provides high-level information to support design decisions earlier in the process. Now, assessment doesn't replace the need for detailed model extraction and analysis, but it will reduce the number of iterations between layout and analysis. It provides the layout engineer actionable information to address obvious layout problems. Assessment can also be used as a sign-off step against the original performance specification. Within UPD, we provide two levels of checking. The traditional DRC engine that will check against the constraint set and our new assessment capability. The third option is also available that provides a seamless pathway to our best-in-class extraction and analysis tools. These tools can be launched with single-click execution from UPD that avoids the delay and hassle of translation and conversions. Now, the assessment functionality in UPD applies our extract-IM technology that quickly identify power and signal delivery issues that could negatively affect performance. Now, we can look for these problems from either the die side of the package or from the board side of the package. The potential problems are intuitively displayed and quantified numerically. Assessment functionality could also be used to document potential issues for colleagues to manage and/or address. This is the type of information we're referring to that can help support design decisions earlier in the process, resulting in fewer iterations and improved cycle time. R&L values can be similar but affected differently by design details. This example shows high resistance on two pins due to thin interconnect to their respective planes. If looking at loop inductance, it tends to be greater for large loop areas where pins are located along the edge or in corners, or situations where pins are isolated with few local nets that can serve as a return path. The power assessment functionality within UPD is presented to the user via a task-focused workflow that will step them through the process of setup, net selection, simulation, and the viewing of results. When we do view the results, we use a combination of intuitive 2D and 3D graphics. Detailed numerical information is also available. At this time now, I'm going to turn this over to Dave West, who will take you through a demonstration of this functionality. Take it away, Dave.
Hi. This demo will show you a simple power integrity simulation using Unified Package Designer, or UPD. On the left side of the screen, you'll see UPD's Workflow Manager. A number of standard workflows are delivered with a product, and workflows can be customized to your specific needs. The current workflow displayed is a detailed workflow for power integrity simulation. UPD's Workflow Manager is similar to the Workflow Manager of Sigridy's other simulation tools. The workflow guides the user through each step of the process, allowing non-expert users to perform complex tasks right out of the gate. The demo design you see consists of a single die, wire-bonded VGA design with multiple power and ground nets. UPD supports many different package styles, including very complex flip chip designs. For this workflow, we'll first quickly review the power and ground structure of the design. This assures the power and ground nets we want assessed are properly assigned. We can quickly view each individual layer and corresponding power and ground structure throughout the stack-up. Next, we'll review the layer stack-up of the substrate. UPD allows you to create a stack-up with any number of layers, easily adding and removing layers as desired. Layer thicknesses and material properties for dielectric constants, loss tangent, and resistivity can also be adjusted as needed. For stacked die type design, the die stacking order and/or component thicknesses can quickly be specified. Since this is a single die wire-bonded design demo, we'll move on to the 3D model setup. UPD supports industry standard 3D wire bond models. Displayed are examples of KNS and JEDEC 3D type models. Any number of models can be created and assigned to groups of wire bonds by either tiers or die or even individually assigned. UPD can quickly identify and correct missing wire bond model assignments. If this design is a flip chip design, we can similarly create 3D C4 solder bump models as well as solder ball models for assignments to die and package pins. Before a simulation can take place, we need to make sure wire bond profiles are not shorted together, thereby causing the simulation to fail. UPD quickly checks all wire bonds for interceptions. It also brings up the 3D view of the package, and the user can explore the design in 3D, and it also aids in the adjustment of any wire bond models that may be needed. You'll also notice in the message window that there are 0 violations reported, so this design is ready to be simulated. We're now ready to perform the simulation. UPD's powerful constraint checker can be used to specify power integrity constraints for loop inductance and/or per pin resistance and inductances that are typically supplied by your IC chip design team. These constraints can be specified on either the net class or on a specific net. While we're in the Constraint Manager, I'd like to briefly point out some of UPD's other constraints. Also in the Power Integrity Rules page, you can see that the setup for UPD's integration to the Power DC tool. And under the Signal Integrity Rules page, there are various constraints for signal net parasitics used by the E-driven flow, which Kevin mentioned earlier. We're now ready to specify the simulation type we'd like to perform. UPD's power integrity flow utilizes extract IM's simulation methodology. The GUIs were designed to be very similar between the tools. These are two types of simulations: loop inductance and per-pin RNL. The per-pin RNL can be either from the board side or is viewed from the die side. The loop inductance simulation includes all power and ground nets, while the per-pin simulation allows you to add the added flexibility of specifying only the power and ground nets of interest. At this point, we're ready to run the simulation. For the sake of time, I'll just import data from a previously run simulation. For this design, the simulation took about 3 to 5 minutes. Simulation times depend greatly on factors of design size, number of layers, number of components, and number of pins. For example, a 10-layer, approximately 2,000 plus pin flip chip design with multiple power and grounds could take up to 2 to 3 hours to simulate. Once the simulation is finished, the results can be viewed in a variety of ways. RL per pin view is a tabulated data showing each pin on the net and associated data to that pin. You can also view the results in 2D view or an RL distribution view. We'll look at the RL distribution view by the net, and we'll also look at the resistance in this case. Here we can see the relative performance between pins on the nets and quickly discover potential problem pins needing further investigation. Hovering over the pin gives detailed information about that pin. UPD's powerful Constraint Manager is a very fast and accurate way to find problem areas of the design. The checker will quickly check for violations of the constraints entered earlier within the Constraint Manager. Detailed information is displayed for each violation. On the canvas, problem areas are automatically selected and zoomed into. This allows the designer to easily find and analyze the problem. In this case, for example, the area fill has been removed for a logo, and as Kevin mentioned earlier, a thin trace now connects to a shared via. For the second violation, we can see there's a similar case where the area fill has been removed. The designer or even a signal integrity person can then easily modify the design to correct the problem area. In this case, we might want to reapply the area fill, stretch it out, or perhaps in this other case, we may want to fatten up the traces. At this point, the user can rerun the simulation to determine how the changes affected the power integrity simulation. I'll now reload the results from a second simulation and rerun UPD's constraint checker. As you can see, there are now 0 violations in the constraints. UPD's power integrity workflow allows a package designer without extensive signal integrity knowledge to design and simulate complex power systems early on in the design cycle. Problem areas often overlooked due to very complex designs and therefore be prevented using the power integrity flow. At this point, I'd like to turn it back over to Kevin, and thank you.
Great, thanks, Dave. All right, let's. So in the next few slides, we'll take a look at some of the other layout capability available within UPD. In addition to the power assessment capability that you just saw, UPD also provides functionality for signal integrity assessment. The SI assessment in UPD applies our Power SI pre-processing technology to produce lumped parasitics. The values are then checked against the SI constraint set and reported as part of the DRC process or in various design advisors. For wire-bonded style designs, UPD provides a very robust, powerful set of functionality to automatically generate the bond shell, along with interactive functions that include push and shove of wires and bond fingers. We also provide a 3D environment to check and model complex multi-tier interactions commonly found on large die with staggered pins or multi-rows of pins or stacked die type designs. For flip chip, we support a wide range of technologies, including build-up substrates using a stack-up similar to like a 3-2-3 type stack-up. We also have some nice capability to manage and route high-speed signals or differential pairs that are fairly common on these types of designs. What's interesting is that we're finding more companies turning to tools like UPD for lead frame design instead of mechanical tools like AutoCAD. And this is primarily driven by the complexity of some of the more advanced styles of lead frames, such as QFNs and VQFPs and even some high pin count QFP type packages. The benefit that UPD provides for this type of technology, the higher degree of automation with the ability to work with electrically intelligent data that has an inherent understanding of connectivity. For SIP, UPD supports a wide range of flat or stacked SIP configurations. The combination of our 3D environment and wire bond functionality makes UPD a very popular choice for this type of technology. We can also support mixed technology configurations where you may have a combination of flip chip and wire bond attachment technology all within the same package substrate. With respect to high-speed design, we have the ability to define a wide range of constraints at varying levels of the design. So for example, we can apply rules on specific nets, groups of nets, we can apply it on a specific layer, and even apply rules to a specific area of the design or area-based type rules. In addition to the diff pair support I mentioned a moment ago, we also support routing rules to enforce delay or length values or to produce matched length routes relative to a clock signal. We also provide some very nice automatic shielding functions that is very useful for critical nets like the high-speed signals and diff pairs. With more designs going vertical, it's important to provide a powerful 3D environment. UPD includes a robust 3D environment that's very well integrated into the layout editor and capable of doing a lot more than just producing a cool image. As a result of our long-term relationship with a number of packaging manufacturers, we have a very good understanding of the fabrication and assembly requirements. And this is reflected in UPD with features that can help improve design efficiency, manufacturability, and yield. So in summary, we've just seen an example of how assessment can be applied to produce actionable information to drive design changes, resulting in fewer layout analysis iterations and providing much greater confidence of a successful package design. Now, in all honesty, this was a very simple example where the problem was fairly obvious. I'd like you to think about your own designs. Think about their complexity and their size. How easy would it be to find similar problems? What additional challenges would exist if you were working with a packaging subcontractor? What would be the impact to the design process and the schedule? This is why UPD and its assessment functionality is needed. The last point I want to make is that all of the assessment functionality, along with the 3D environment, SIP support, lead frame support, This is all part of our standard UPD product, which makes it a very good value proposition. I'd like to thank you for your attention at this point and would be happy to take any questions.
Okay, great. Thank you very much, Kevin, and thank you, Dave. We have had a number of questions that have come in, and so I'll go through some of them now, kind of grouping them up a little bit by topic. So one of the ones that came in early on in Dave's demonstration was a question about where the constraints come from.
Okay, I'll take a shot at that. Where the constraints come from is the values for per pin resistance and inductance are usually provided by the chip design team, more likely by an SI engineer or someone like a system architect. Now, these values are usually determined from chip static or dynamic power simulations performed for new designs. One of the other things that we see sometimes is that they're based on actual performance of no good values of previous designs, previous generation type products.
Okay. So another person asked a question that kind of goes along with this topic. He's asking about whether or not it's possible to have UPD take in a script as input to allow the rules to be entered for these constraints.
Absolutely. UPD provides a very powerful environment where you can load in various scripts, various macros and such. So yes, this is something that could be easily scripted and to some extent run in the background, so to speak. And then when it's all said and done, you can go in and evaluate the results.
Okay. Okay, great. This same person asked a flow-oriented question, and actually I'll take this. The question is whether or not any of the edits can be back annotated into Allegro APD. And actually the comment that I would make about this is that like Allegro APD, Sigridy's UPD is really an industrial strength package layout tool. And so if you receive a design in an APD format, there's a way to get it into the UPD environment, but you wouldn't use it as part of a highly integrated flow with APD. And similarly, if you do a design in UPD and have a customer that needs a format in APD, that can be accommodated as well. So for companies that have an APD flow, the analysis tasks that were described by Dave could be performed in our Extract IM tool, but it wouldn't be nearly as interactive. So since that topic kind of came up, sort of touching on this Extract IM area, which is a product for package extraction and assessment, maybe I'll go to a related question, which is, can I generate IBIS or SPICE models using UPD's analysis functions?
Okay, Leslie, I'll take that one. The short answer is no. Our assessment functionality performs a detailed analysis much as it would for model extraction. However, the analysis performed is faster and much more memory efficient than it would be done for the actual model generation step. In that case where you do want models, you would use the Extract IM tool to generate those models, which is accessible directly from within UPD, kind of in that single-click execution mode I talked about a little bit earlier.
Okay. Okay, and then could you comment about how the accuracy of the assessment functions that you've shown inside UPD compare to other Sigridy products? Sure,
it's a fairly common question. The assessment shown today is based on the same highly accurate type of analysis that Extract IM applies to generate the SPICE and IBIS models. The only approximation made in these analyses is for per-pin inductance. Since current must flow in loops, the return for each pin of a given net is assumed to be in all the other pins of all the other nets. Now, this is a technique Sigridy pioneered some time ago for Extract IM and is proven to support electrical performance assessment for a very wide range of packaging families.
Okay. And then one last question. Certainly we're open to others, but one last question I'm seeing here is a person is asking if we could comment on who a typical user for Sigridy's UPD, who would that typical user be?
Well, that's changing. If I look at a few years ago, it was primarily layout engineers looking at the physical implementation of the package, and that still represents a good portion of our customer base. But what we're finding now is more analysis-oriented people utilizing UPD, the ability to go in and take a layout on their own, make some subtle changes to it, much like we saw in Dave's demo where we changed maybe some line widths, maybe make some subtle changes and be able to iterate over that on their own. One of the things that's nice about UPD, as you hopefully have seen, is that the UI is very similar to the other Sigridy tools. So the learning curve for UPD is quite short if you're familiar with tools like Extract IM or Power SI. So we're starting to see, the use of UPD expanded, not just in the layout phase anymore, but also into the more analysis-oriented user that wants to do what-ifs and kind of do some trade-off type scenarios. So it's definitely changing.
Okay. Very good then. I think we will leave it here for today's webcast. I appreciate the contribution by Kevin and Dave West, and mostly by those of you who have joined us today. So thanks a lot, and we'll look forward to answering future questions that you have when you contact us outside of this event. So thanks a lot.
Great. Thank you. Bye-bye.